Hi. There is some technical problem, and give me 1 minute.
Okay, no problem. I'm here. So, okay, so we got that. At least I was hoping I hadn't messed up. I said the host hadn't started the meeting or anything. So.
핸드폰으로 일단 네, 이거 어떻게 처리되지? 예? 핸드폰은 괜찮지 않나? 그래도 핸드폰 패널이고 Andre, can you share your slide?
Yeah, can you hear? Yeah, I can hear you.
Can you you will using the some record? I mean the document.
Yeah.
Okay.
Yeah. So that's what I'm gonna. I mean, this is the way I've been teaching on Zoom. So I gotta try this out.
Yeah. Okay.
Can you look at it? Can you read it? Is it too? I can adjust it if it's too small or something like that. Or?
I think it's okay.
Okay. All right.
Okay.
Well, let me know when I should start, I guess.
Okay. Yeah. No.
Okay, now I can see you guys. All right.
Yeah. Okay. Yeah. Yeah. We will
Hey,
start.
yes. Yeah.
Hi. Yeah.
Hey,
Let's
Shanghai.
start. Yeah. So we will begin the last day session of our workshop. The speaker is Andre LeClair. He will discuss the TTbar deformation of the Ising model and ultraviolet composition.
Okay, thank you, Chandra. Thank you for the invitation. I'm kind of new to this topic, so I've learned a lot already, and I hope I can contribute, even though, like I said, that this is kind of based on some pretty recent work. So this wasn't the title of my talk, it's the title of the conference, but could just as well be the title of my talk. The talk was about TTbar ultraviolet completions on the Ising model, which is I'm just going to get to toward the end. So it's based on two recent articles, of course, in the archive from last spring, okay, to be published in JSTAT and Journal of Physics A. So here I'll only be talking about 2D integrable theories, okay, which is the main context for these for this subject. So at the beginning, I think for this crowd, probably I'm going to review a little bit too much of the obvious, but maybe it'll just serve to to show you what sort of an emphasis I'm taking on the topic. All right. So what is it? I think of it in terms of an action. So take S0 here to be quite general. It's an action for an integrable 2D QFT. It could be a massive theory that's integrable, factorized scattering, or it could be a conformal field theory. I'm actually going to talk about both, but ultimately I'll be more interested in the case of a conformal field theory. Okay. So what's interesting about these perturbations, one thing is, well, certainly that every theory S0 has a stress energy tensor, and you can always consider this kind of perturbation by TTbar here. I just mean these are the components of the stress tensor. To be a little more specific, this is a massive theory. You have to include the trace here, but I think everybody here knows that. So the point is it's an irrelevant operator, dimension 4. So alpha has units of 1 over mass squared. Okay. So why is it interesting? There's two reasons that are kind of different. First of all, it arises in string theory. And I think these are some of the original works on the subject by Dubovsky, who talked yesterday, Cassel et al., which Tateo was one of the authors here. In fact, some of my stuff I'll be talking has some overlap with these very early works, although it's in a kind of different formalism, I would say, that's more general. So that's one major application. It seems to be just a great, at least half the interest in the subject is in that area. And then there's the pure quantum field theory level. And there's some basic questions here, how do you make sense of an irrelevant perturbation? And this is the point of view that the take I took on this subject and why I found it kind of interesting. Sitting for 30 years at Cornell in the particle theory group, I mean, you see, really, if you pull yourself back from it, you see that all this beyond standard model physics, quantum gravity, etc. It's really all an issue about, well, we know very well a low energy effective theory that is ultraviolet complete, what we call the standard model. But to go beyond, usually you consider some irrelevant operators. Just think of quantum gravity. I mean, it's really a theory of, think of it as a theory of massless gravitons perturbed by some irrelevant operators. And you're trying to understand quantum gravity is a bit about, well, a lot about what is the ultraviolet completion of such a theory. Okay. So there's two communities, string theorists, and then people working pure quantum field theory, integrable quantum field theory. They have rather different perspectives, I think. So what are some of the important known properties? Again, this should be pretty well known to everyone. Most of what I know as far as the formalism comes from these two papers. Smirnov and Lozhkov and Kalogyev. Again, the Robert Berta was one of the authors in this paper. Well, turning on the TTbar perturbation does not ruin the integrability. It's very interesting. And a lot of the focus is on the ground state energy, or if you like, excited state energies on a cylinder, an infinite cylinder of circumference R. Okay, so we talk about E of R as the ground state energy. And one of the most general results quite independent of a particular model is this so-called Viscount-Burger's equation satisfied by the ground state energy. So this has, of course, many, many solutions, depending on what theory, initial conditions, well, what particular theory you're talking about enters into the initial conditions. But it's readily solved. This differential equation, actually mathematically can solve it. The other important fact is that the S matrix, so if you have the S matrix for the unperturbed theory, then the S matrix is dressed with a C to D factor of a very simple form of this the IG sig theta, rapidity space. Okay. So theta here is rapidity, parameterized energy momentum in 2 dimensions. So G here is dimensionless, it has to be, so it's essentially proportional to your alpha times m squared, which is dimensionless. And I'll fix, with the conventions I've written so far, this is just going to be a minus sign. This will be equal up to a minus sign. So, okay, so one of the more interesting features, and not in all cases, as I'll describe, but in most of the interesting cases, this ground state energy develops a square root singularity at short distances. So the theory cannot be taken down to ultimately to arbitrarily small distances. In a sense, the ground state energy becomes imaginary at short enough distances. So that's defined by a certain scale R star. So again, here's the perspectives of the two communities. The string theorists, I think, would say, well, of course, the ultraviolet is a string theory. It does have a minimal length, and essentially the string scale. And once you get to that scale, then you're talking about string theory, which is non-local. Okay. I think the original context of this TTbar perturbations, like Dubovsky et al. And the other Cassell et al., mainly came from string theory. Then the quantum field theorists would say, well, again, would say, of course, this is just the usual sickness of irrelevant perturbations, that we learn about in graduate school. Irrelevant perturbation, you end up generating an infinite number of additional couplings with more and more irrelevant operators, and things get out of control. Right? Relevant perturbations, usually in any quantum field theory, there's a finite number of relevant perturbations, so things are in control. But anyway, so these are interesting questions, and probably there's more to this story than just this. And I think part of the interesting aspect of this research is trying to bridge the gap here. I just want to mention a very early precursor to some of this stuff with an old paper. Actually, I'm giving this talk from Trieste, so my friend Giuseppe, certainly it wasn't TTbar, and at the time they just were interested in the TBAs, thermodynamic ansatz, with the wrong statistics to see what goes wrong. And in a sense, they saw a lot of these kinds of singularities there. What exactly their model was is not completely clear, but formally, some of the things they saw were similar, and they recognized that what they were doing was some kind of irrelevant perturbation in Ising. Which one, not clear. I'll be a little specific about my perturbations. So this is not going to be the main example that I'm going to work out in detail, but it motivates the kind of issues that come up So let me take the unperturbed theory, sort of as zero as just the Sinch-Gordon model. It's probably the simplest integrable theory. There's one scalar particle. This S matrix is known. And in a sense, this S matrix is a CTD vector. Okay, but we're interested in perturbing it by TTbar. Okay. So qualitatively, what do you expect? Well, you have a competition here. I mean, look, the cosh phi term is relevant, and the T-bar is irrelevant. So at very low energies, well, these are called irrelevant for a reason. Very, very low energies, this T-bar doesn't matter. And you're just talking about the ordinary Sinch-Gordon theory. At the lowest possible energies, the mass of this Sinch-Gordon particle is, well, essentially infinitely heavy. So everything kind of decouples and you're left with something that's empty. You know, so the Virasoro central charge would be zero here. Okay. The ultraviolet, well, it's the opposite. Very, very high energies, the TT-bar becomes more important than the relevant perturbation. So in fact, at the highest possible energies, lambda, here the coupling is going to zero. And then we're just talking, well, essentially you have the ultraviolet limit of Sinch-Gordon by itself, which is the free boson, perturbed by TT-bar, which was, in string theory, this was the first kind of TT-bar perturbation that was considered. So it's the ultraviolet that is the most interesting region here. But there's an interesting crossover. Let me sketch here C of R, which is its effective Virasoro central charge, which I'll just, if you need to be reminded, I will remind you in a moment. But let's plot this as a function of 1 over R. So very, very large distances at the origin here. So down here, this is just Sinch-Gordon. You can ignore the TT-bar. If there's no TT-bar at all, the Sinch-Gordon theory has an ultraviolet fixed point at C equals 1. That's the free boson. But there was no TT-bar, it would just end there at arbitrarily short distances. But there is a TT-bar which kind of takes over, and then the effective central charge flows off to something else. Over here, this is somewhat boring here. This is the interesting part. There's quite a lot known already. Notice I plotted C to be increasing. This is toward the ultraviolet here, is down this axis. So I'm gonna usually have something called the c-theorem that tells you the central charge in unitary theories anyway, that central charge should increase. So that's how I've drawn it. But there is a crossover region. And they could, yes, yeah.
So if I turn off TT-bar, just consider Sinch-Gordon model, and then if you take a UV limit, then you are saying that it's a free boson theory.
Yeah.
But actually, if you analyze the TBA of Sinch-Gordon model in deep UV region, actually you are looking at some Liouville conformal filtering structure.
Yeah, that's that. I mean, if you look at the TBA for just pure Sinch-Gordon and extract the ultraviolet limit, you get C equals 1. I mean, that's
yeah, C equal 1, but actually it's not free boson. And
well, yeah, okay. I mean, there's corrections, of course, but I'm saying if you go all the way to to arbitrarily short distances, okay. I know what you're saying. You're saying so the deep ultraviolet is a relevant perturbation of C equals 1. Okay, that's definitely true. but it's a relevant perturbation. So in the deepest ultraviolet is just a free boson. Okay. But anyway, this crossover, this whole flow could be under quite standard methods to track it, which is will be thermodynamic beta ansatz. So here, this effective central charge is a way of parameterizing the ground state energy. These normalization factors are such that for a free boson, this C is 1. So, and you know, having this C to D factor just modifies the kernel in a very predictable way. You follow the standard prescription. So this could be studied in some detail. That's not what I was so interested in. I was interested in the ultraviolet limit. So actually, my contribution was essentially kind of general prescription for taking the massless limit of some integrable theory that's massive, and it's a little unexpected. I mean, this massless scattering is something invented by the Zamlodchikovs, and it's not on completely firm footing. But here we have it checked. You know, whatever prescription you come up with, which I feel was not in the literature before, but perhaps in his early papers by Cassel et al. And Bobsky, it was kind of hidden in there because they did get the right kind of ground state energy. Well, from a modern point of view, in terms of rapidities, etc., this was kind of my contribution, and it was very useful because it kind of gave a way of thinking about ultraviolet completions. So for now, let's just forget about the cinch board. We're just going to be interested in the ultraviolet limit, which is a CFT perturbed by TTbar. And we're interested not just in the free boson. We want to get something that's more general. So one way to do that is, first of all, allow your particles to be either fermionic or bosonic. Something that the TBAs differ by signs. And just to have a larger playground, I would like to have a continuously varying central charge in the infrared. Now, so I have a conformal field theory perturbed by TTbar. The conformal field theory has some central charge I'm calling CIR. And I'd like that to range between -infinity and infinity to cover all bases here. And there's a simple way to do it that without specifying some details of a particular model. This was kind of motivated by thinking about Liouville, but I'm not sure there is a connection with Liouville in the end. It remains to be seen. Certainly, I didn't make a strong case for that. But it turns out that just adding a chemical potential to the free TBA of bosons or fermions can cover the whole range of infrared central charge. For C less than 1, you need bosons. For C above 1, you have to replace the bosons with the 2 fermions. Okay, so the TBA differs there, but they match up at 1. And Z here is going to play a role in the TBA equation. It's just the standard fugacity, which is E to the chemical potential R. No, I forgot to write down this formula here, but using dilogarithms, for example, you can figure out what Z is as a function of C. Okay, but the formula is not so important right now. So what's this factorization talking about? It's really quite simple. So the C-D factor, remember, in this pure TTbar perturbation. I'm not going to address things and look at more general CDD factors. I'm just going to go with the pure TTbar case, which we know is this. And it turned out that if I just follow the standard prescription of TBA and just try to plug this in to the TBA equations, the solutions don't converge. So one way to make it converge was to factorize this into left-right and right-left scattering, where you just split the sinh into two exponentials. So right-left is the IG e to the theta over 2, and left-right is the other part of the sinh, which is minus IG, the minus theta over 2. Okay. Seems a really simple prescription, but if you look in detail the TBA equations, which I write down here, with these particular kernels, remember the kernel is generally minus I times the derivative of the log of the S matrix. Okay, so the kernels are just G over 2 e to the theta, or minus theta. And if this is the kernels that appear in the TBA equations, and these integrals converge. Okay, so these things, you just write these down once you know where the kernels are. You have one particle, boson or fermion, that's encoded in a sigma. Sigma plus 1 is the boson, and sigma minus 1 fermion. Then we have a chemical potential, which appears here, Z. And little r is big M times well, it's the mass of the particle. It's big R. Well, it's not the mass of the particle here. This is massless scattering, but it's you need to set an energy scale for particles. This is M. So it's a little r. And if this is just pure conformal field theory, basically these kernels would be 0. And then these are your pseudo energies, and it's just a free boson or fermion. I didn't write the formula for the central charge, but throw away the kernels, you're going to get C equals either 1 or a half, depending on bosons versus fermions. Okay, so the TBA, usually TBA equations can't be solved. But because of the form of the kernel, notice, remember the kernel, this is a convolution here, but the kernel is again proportional to e to the theta, which is the same thing here. Okay, so your pseudo energy is just some function times e to the theta, and similarly for the left movers. So the TBA equation just becomes algebraic. And you get the result that is an old known result, which you can get, say, from the Burger's equation. So the formula for the effective central charge, then, I like to write in terms of this dimensionless H, which is minus the alpha coupling for TTbar over R squared. So that G that appeared in the S matrix, the C to D factor, is just minus alpha M squared, which is dimensionless. And then there's this rather standard form. If you put this into the equation for the pseudo energy, you can manipulate it into the ground state energy, you can manipulate it into the formulas that you've seen already at this conference. Okay, so let's since we have this variable central charge, let's try to look at possible RG flows. Okay, again, as somebody say interested in quantum field theory, I'm interested in ultraviolet completions. And well, it turns out that depending on what your initial central charge is, there could be or there could not be an ultraviolet completion. So now the parameter space is a bit large, not huge, but just to limit the possibilities, I'm just going to impose that the central charge increases toward the ultraviolet. There is demological c-theorem. For unitary theories, this would be the case. It's not clear at all that it's relevant here because, you know, if the ultraviolet is some string theory, some non-local theory, then it's not even clear there is you can formulate a c-theorem, because c-theorem does require that the assumption is you have some ultraviolet theory to begin with, you're perturbing irrelevant operators, and you show that c decreases toward the infrared. But it's still worth just listen. You don't have to impose this, but it's interesting to impose it because in many physical examples, this is what should happen if there is an ultraviolet completion, is that C should increase. Anyway, that just requires that alpha is negative or G is positive in my conventions. Or did I get it backwards? Wait. Negative. Oh, I might have gotten this backwards. Okay. No, wait. Let me see. No, okay. I want G positive. Yes. Okay, I want G positive, which alpha is negative. I believe that's right. So in any case, what happens in the ultraviolet just depends on what the infrared central charge is. Okay. Okay. So if alpha is negative, wait, right? Yeah. Okay. So here H here is positive. Okay, good. Okay. Okay, H is positive, but if the initial central charge was negative, then this would never develop a square root singularity. Some signs sometimes. It's easy to flip. So in any case, if the initial central charge, let's impose a c-theorem, just to limit ourselves, and if the infrared central charge initially is negative, which is certainly possible, then in the ultraviolet, now you start somewhere here. This is 1 over r again. Infrared is here, so there's a line of infrared fixed points. But anywhere where C infrared negative flows to C equals 0. They all flow to C equals 0.
Sorry, may I have a question?
Yeah.
So this c-theorem puzzles me a little bit because in homological case, he's really considering the usual RG flow, where you like integrate out some degrees of freedom when you go from IR to UV. But the TTbar deformation is a very different type in the sense that it stays from to states. It doesn't create new states or integrated out states. So I don't see why this comparison is valid.
Well, I'll give you sort of my main example. One of the sort of punchlines here. I mean, we already know a TTbar perturbation that is ultraviolet complete, which is the TTbar perturbation of the Ising model. You know, if you add other operators, then it does in the ultraviolet. It is a different conformal field theory. So if you're thinking, well, when Zamolodchikov's original c-theorem, you're thinking from the top down. You start in the UV, you assume you have a well-defined UV theory, which is some conformal field theory. You perturb it by relevant operators, and then you flow down to the infrared. We're starting in the infrared. We're starting the other end. We're trying to go backwards. Okay, so it's very consistent and interesting to ask, given a TTbar perturbation, can I go backward? Backwards. Can I go toward? Can I figure out what's going on in the ultraviolet? All right. Now, as I emphasized, the c-theorem doesn't necessarily there isn't necessarily an actual c-theorem for all these theories because, well, if the theory is not defined in the ultraviolet, then I don't think you can formulate a c-theorem. I'm just imposing this just to limit the possibilities. I wouldn't have to have 4 graphs, it's just 2, all right?
Okay.
Now in the, so,
may I
well,
ask one more question?
What?
May I ask a question? So
Yeah.
here central charge is negative. Does it mean it's non-unitarity, or is there some problem of negative central charge, or
Well,
maybe
I'm not specifying in detail what this theory is here. Okay, so then you have to get more specific. Remember, I just turned on a chemical potential to move along this line. Right? But kind of interesting, I think, because, well, for instance, if the infrared central charge was 0, of which there are many interesting examples, like polymer, like percolation, then the infrared and ultraviolet central charges are both 0, which would mean there's no flow at all. So this would seem to suggest that for something like percolation, the TTbar perturbation actually does not break the conformal invariant somehow. But that's something I didn't really explore in very much detail. I'm more interested in, but I think there's still something to be understood. You know, why do all these theories flow to 0? And this is a TTbar perturbation. Okay, so there are some TTbar perturbations. If you're starting with a negative central charge, you're going to flow to z equals 0 without any string scale. So these are presumably not string theories. How much time? Okay, I think I'm doing good on time here. The more interesting ones, of course, are the singular flows, which are in the very early context of Nambu-Goto string, etc. This is what was encountered. Where here, I assume the infrared, the central charge is positive. Okay. Well, that's the situation for the Nambu-Goto string, because you thought the string theory is a free boson. So you're talking about c equals 1, say here. And in this case, when you try to go to arbitrarily short distances, that square root develops an imaginary part, so you really can't flow beyond here, so beyond some scale. The theory, the central charge here is still finite. It turns out to be twice the infrared value. But the beta function is not 0 there. It's definitely not a conformal theory. Okay. But actually, in my paper, I'm not going to go through it now, but in my paper, I explored this region. You can look at the TBA and expand about this point and figure out the dimension of the operators that are sort of pulling you out away. So, I mean, you can think of starting here. It's not a conformal theory, but given this somewhat singular theory, you can ask what operators are kind of pulling you down to the infrared. Turns out to be a very generally turned out to be a dimension 3 operator. And I don't have the interpretation of that yet, but it's not a very hard calculation to do that, to ship that. Okay, coming to the last part of the talk, which is the more recent, it was the second paper on the subject, which I think addressed a kind of fundamental question, and the answer was a little bit surprising. So this is a question that, you know, is fundamental particle physics, you know, faces. You know, given a low energy theory, that works, and plus some irrelevant operators, either you give up, or if you're trying to deal with quantum gravity, then somehow you have to deal with this situation. How is there a prescription for completing it in the ultraviolet? And certainly for decades, I think most people would answer no. because of the standard reasons that you generate more and more infra-red operators, non-irrelevant operators, and then you have an infinite number of couplings and you lose predictive power, okay? Which is, in a sense, still true. But there were some ideas about this, you started with Weinberg. You know, some people in the quantum gravity community talk about asymptotic safety. So they think, well, maybe general relativity, even though it looks like a bunch of irrelevant operators, you know, maybe there is, you can't see it, but there's actually an ultraviolet fixed point somehow, so that you never really get to ultimately short distances. So that would kind of save all the problems of quantum gravity. And there was quite a few years people pursued that. I assume they probably still pursue it. They can refer to it as asymptotic safety. That's one thing. But I'm going to try to be more specific here. Here where we have integrability to work with, and which helps. So this question, I think, is pretty well posed. How can you complete it? You know, ultraviolet, is there more than one way to complete it? What's the role of symmetry here? Okay. So, well, the natural thing to do, you know, as I said, I mean, the general thinking is that if you start with an irrelevant operator like TTbar, you're going to generate many other irrelevant operators. But, you know, Zemlyatkov and Smirnov gave us some important information. In addition to TTbar, there you can build operators out of the other local integrals of motion. So they're labeled by a spin S, which is an integer, because they're local. So this operator x1 is what is TTbar. In quotes here. Okay. So I'm not writing out the trace parts. But there's an infinite number of them, which we label. They start, if it was a conformal field theory, you just label them as T bar, labeled by the spin. Okay. So for instance, in the spectrum of these integers, depends on the model. Simple models like Ising or Gordon, S is an odd integer. For Ising model perturbed by a magnetic field, then turns out the spectrum is related to E8, and then the spectrum of these spins is related to some properties of E8. So not all integers are covered. Typically, they're still odd though. Anyway, Smirnov and Zemlyatkov told us that all of these preserve the integrability. So there's actually potentially a vast space here of integrable theories. They're not all going to make sense, but they're all integrable for any choice of these couplings, which is kind of surprising. And they also told us that the CDD factor is still quite simple. It's still an exponential. Before it was just G sinh S theta, but now it's sums over G sinh S theta. Surprisingly, S is kind of a spin. Okay, so spin one, you think of energy momentum, that's sinh theta, but if you have some higher conserved current, then this S might be 3. Okay, but there's the form of the CD factor. And well, this is where this prescription that I came up with was very helpful. So I'm going to get very specific now, look at the Ising case. So the infrared central charge is 1/2. We know that the local integrals of motion, it's a free theory, so I mean you can construct them. We don't need their explicit form, but the spins are positive integers.
What is relation?
Is there any
What?
relation between alpha S and GS?
Wait, say that again?
A relation between these alpha S parameters in the action and the GS parameters in the S matrix.
Yeah. Well, you certainly know that. Yeah. I mean, by dimensional analysis, GS has to be proportional to alpha S times M M to the 2S, I guess. I mean, there's a constant proportionality there, which we're going to fix. But these G's are dimensionless. You have all these irrelevant perturbations, so you know the dimension of alpha S. Okay, so for just TTbar, you're talking about alpha 1, right? And that's just alpha.
That's obvious. That's obvious.
Yeah. Okay,
but this
so
proportional constant is independent of S.
No, it not. Well, it doesn't have to be. But I am going to. In my case, it won't be. Okay, it won't be. Right. I mean, here it is. Okay, here it is. Okay, what I wanted to do was, I figured there's probably an infinite number of irrelevant operators. Generally, it's what happens. So I'm going to include all of them. Then, well, I want a continuous parameter like the standard TTbar. All right, standard TTbar, you have alpha. It's a continuous parameter. And G is just alpha m squared, or minus alpha m squared. So I want a continuous parameter. So I'm going to choose this. Okay. And the reason is that now I follow my prescription for massless scattering, massless TBA. I can still factor this thing, right? Because the singes can all be written as the sum of e to the exponential plus e to minus that exponential. I factorize it the way I did for just pure TTbar. And then, for say positive rapidity, this actually converges. Okay, and it gives a kernel that is quite simple. It's G over 4 divided by cos theta. Okay. So before we had, remember our kernel was, without massless scattering, etc. The kernel for the pure CTD factor of TTbar, it was cos theta, which kind of leads to some of the single behavior. Cos theta, as theta goes to infinity, blows up. So here, with this particular choice of couplings, I'm kind of fine-tuning a bit what the couplings are of irrelevant perturbations. Okay, and I got this simple kernel. All right, and well, I can ask, well, what S matrix did it come from? Well, it turns out that if you take this simple S matrix, which is like a CTD factor itself, as 0 as a tanh, theta 2 minus pi over 4. Well, to get the G over 4, you raise that G over 4th power. Okay. Now, for G in the original TTbar, remember G is just some arbitrary irrational number. For arbitrary irrational number G, this S matrix looks peculiar. It's probably going to violate some kind of analyticity property. Okay, so it's kind of obvious that G equals 4. Well, any multiple of 4 could be a good theory, right? Because then it's just a product of an integer number of these basic building blocks. All right. So
can I have a question?
What?
So this G parameter is somehow can be considered as this proportional constant between GS and alpha S?
Yeah, yeah, I mean, this G, well, when you turn off, well, look, if you turn off all of the other irrelevant operators, right? This G is just minus alpha m squared, where m is the energy scale that appears in the massless TBA. Okay. But for the higher spins, again, just by dimensional analysis, you want.
I see.
So I'm fixing out S. So in a sense, there is these algebraic numbers here, you know, the minus 1 n to n plus 1. But I don't want to introduce an infinite number of continuous parameters. I want to introduce one that I can match up to the standard pure TTbar. Okay. I didn't have to. This could have been, I could have had some other numbers there. But I thought this was the most natural thing to do, that at least for, we can match, if you turn off the higher relevant operators, we can just match on to what we, the standard TTbar. Okay. So for the first one, n equals 0 here, then we just, this G is just the standard alpha pure TTbar.
Yeah, so that means that I can increase G. I can control this parameter G by just making alpha to be bigger, right? You know, the coefficient TTbar. Alpha, if I increase alpha more and more, and then G can increase also.
Yeah. Yeah.
So it's just a kind of a controllable parameter in which is actually coefficient of TTbar.
Right, right. But then it turns out once you go through this, you see that, you know, I mean, you know, this factor here raised to the 1/3 power, I would think is probably, I mean, it satisfies all the constraints of a CDD, etc. You know, because this as a CDD factor satisfies the constraints of CDD factors. But you know, this S matrix raised to the 1/3 power is probably sick for reasons of analyticity. So anyway, already just from this expression, you see that multiples of 4, integer multiples of 4, are potentially physically relevant. Okay. Then it turns out, so you study your TBA and you try to see if there's an ultraviolet limit of this TBA. And it turns out that for G bigger than 8, there isn't. Okay, there's no, well, if you remember your massless TBA or regular TBA, if you're trying to extract the ultraviolet limit, you have to satisfy this transcendental equation involving laws and etc. And then the ultraviolet symbolic charge is written in terms of polylogarithms. But I think that's a pretty standard thing, so I'm not going to take the time to go over that. But so we're kind of pushed to G being 4 or 8 here. Okay. And no higher. This is a bit what theory, the talk we heard by Tiago, where remember he considered multiple CDD factors, and they didn't notice that, you know, if there's too many of them, and it was about 2. If there's too many of them, then there's something wrong with it. Theory. Okay, but here it's quite specific. Okay. So, well, for people who are, you know, from the old days of integrability, they'll recognize the G equals 4 case is the famous flow from the tricritical Ising model down to the Ising model. You can do a pretty standard calculation. Now your TBA equations are pretty non-trivial. Still, I mean, with this kernel, you know, it's just 1 over cos theta. I mean, there's no explicit solution. You have to do quite a bit of work to, in the infrared it's easy, it's just Bessel functions and more and more Bessel functions. But the ultraviolet requires some amount of work that was was originally developed by Affiliation with some logical. Anyway, we get C equals 7/10. So in a sense, well, I mean, if you're part of this old community, you would say, well, that's not surprising. Affiliation and logical already knew that the flow from tricritical Ising down to Ising arrived at Ising through TTbar. It was not easy. Yeah, I think he said so explicitly in his paper. All right. But in a way, let's imagine we didn't know that. I just kind of followed my nose and tried to add some preserve integrability, add some irrelevant operators, more and more of them. And I just ended up following consistency and sensibility, ended up with this G equals 4. Then I go ahead and do the calculation of the ultraviolet single charge, and I would have found 7/10. You know, so in a way, I could have rediscovered this completion from the bottom up. Okay, so I thought that was kind of interesting, but this case we knew. Well, what makes it a little more interesting is that at least there's another case. If this is all we found, well, then maybe the top-down approach is telling us more. So anyway, like I said, this flow is known, but when you take G equals 8, which is 2 factors, it's not a double 2 copies, you still have 1 fermion, then the ultraviolet sum charge turns out to be 3/2 if you do the same calculation. So this coming from certain identities from the Rogers Pauli logarithm, which is what leads to something rational like 7/10. So the same calculation here gives you 3/2. And what I found kind of remarkable is both these theories have supersymmetry. C equals 7/10 is the minimal n equals 1 supersymmetric minimal model. And C equals 3/2, well, just a free boson, and the Majorana fermion has C equals 3/2. And it's actually the top component of the minimal n equals 1 minimal theory. So this is the lowest one, this is the top one of this minimal SUSY theory. So without building in SUSY, in fact, the Ising model has no SUSY. So, you know, so the SUSY only appears in the ultraviolet. Well, apparently, it's spontaneously broken. Alyosha's and Logikov interpreted the Majorana fermion as a so-called Goldstino of this spontaneously broken SUSY. By the way, the SUSY kind of popped out. It wasn't built in, and it makes things kind of interesting. So I'm just going to finish with some open questions. So, is there a feasible classification program here, where start with a conformal field theory, perturbed by TTbar? Just pure TTbar may or may not have an ultraviolet completion. It may just be some non-local string theory that you're finished, nothing to think about more. But if you want to just stick with local quantum field theory, you can ask, what are the possible ultraviolet completions? Now, you know, we're assuming we're adding integrability into the seed theory here, but so integrability is helping. Supersymmetry kind of came out in something in the ultraviolet. We didn't put it in, but somehow it's playing a role here. This kind of helps bolster some of the beyond standard model people who for many decades loved supersymmetry. This is sort of getting it from the bottom up again. Well, when I wrote this paper, I was about to do more work on it. But I kind of got busy with some other things, but I'd like to a little bit more about this C equals 3/2 UV theory. Right? It's not so hard to do to figure out what relevant operators are driving you out of ultraviolet. Okay. So then we have another question. That final question is, TTbar has come to mean some rather general things. So one is TTbar string theory versus a well-defined quantum field theory. Right? Not all, it's kind of clear, I think not all, in some more recent papers, we just look at some C to D factor and interpret it as a TTbar perturbation, but then it could have singularities, and then, well, is that a string theory or is it just a SIC theory? That's an open question, I think. Not every CDD factor, even for perturbations of free theories, not every CDD factor has a well-defined ultraviolet completion, number one. And if it doesn't necessarily correspond to a string theory. Okay, so what, this is a huge class of theories. Some of them probably don't mean anything. Okay, but some do and some don't. And trying to answer this question, I think it'll be interesting. Okay, so I think all right, the timing is pretty good. All right, I'll finish there. Thank you. Okay, let me turn on.
Nice
Let me try to go back to.
Yeah. Is there any question? Yeah.
So it's your G=8 case.
Yeah.
So you are saying the S-matrix is basically square of this tangent hyperbolic.
Yeah. Well, it's not. I don't know if I heard the question. Maybe I should turn up my volume here. You said you're asking if it's a pair of. No, it's not. It's not. If I understand the question, maybe if I don't answer it right, then repeat the question. But it's true that G=8 versus G=4. The G=4 just has one copy of this S matrix here, and the other one has a factor as this squared. But it's not two copies in any way. Is it two copies of the first one, because you still have one particle. Okay, so you still have one particle. S matrix is different. It just happens to have two factors.
Yeah, it's not two copies, but S matrix itself is the square of this S0 when G=8.
Wait, say that again, Shangru?
Yeah, so if G=8,
yeah,
S matrix is square of S0.
Yeah, it's the square of yeah.
S0.
Yeah.
So and then this generates the UV supersymmetric series.
Yeah. For some reason, it was definitely a surprise. I wasn't really expecting anything really, but yeah. I knew the 7/10 was.
Yeah.
But
do you know what is conformal field theory? What is this supersymmetric conformal field theory?
Well, you're the man to work on that. Like I said, I was kind of last spring. I was kind of in the middle of trying to do that. It's not that hard, but I got busy with some other stuff. But it's a very natural question. What is this theory? Here we know, because you're coming from tricritical. Well, the ultraviolet is tricritical, Ising. And what relevant perturbation is? The phi 1,3 perturbation in the minimal models, right? That takes you down to Ising. Here, what you have to do is just control the ultraviolet TBA and figure out what this theory is, I think. It could just be, well, look, CUV is 3/2, right? So it should be easier. It should just be should be just a free theory, a free boson and a free Majorana fermion. And then you have to perturb by some relevant operator. There's not that many options here. It could be some kind of Yukawa coupling. But the claim would be that this does flow, will be integrable and flows down to Ising, directly to Ising. It doesn't stop anywhere in between in some other supersymmetric model. So this flow is pretty well understood. This one, it seems to be a prediction of this approach, but what exactly this flow is not.
Yeah, so I know one supersymmetric conformal free theory which flows to Ising model.
Which one?
So long time ago I collaborated with Alyosha, and that is a flow from super Liouville theory, which has also central charge 3/2 to Ising. And the S matrix is actually S matrix of this Goldstein. The only difference is that the S matrix is different from this square of S0. So I'm sure that this what you found, this S matrix you propose for G equal 8 should be something different.
Well, I mean, send me the reference. I'm sure it's on the archive.
Yeah, I'll send you. Okay. I know. I mean, about 20 years ago. I don't know exactly.
Yeah, because I know you worked a lot on this. But well, you started this at Cornell with me, the super Stein Gordon, right? So
no, different. That's super.
I know this is different.
Yeah, I know. But that's massive theory. Okay. But we are talking about here massless theory.
Yeah. No, I'd like to look at that. Like I said, I mean, I think this can be worked out. I just haven't gotten around to it. Maybe it's hard.
One idea is that you analyze this near UV properties of this TBA and see what is this relevant deformations.
Yeah,
that's this deformation. Okay.
Yeah. I think I wrote that somewhere here, but like I said, that was sort of my next project in this direction. Well, I guess I wrote it here. Yeah, more detail. What is the relevant operator in the UV? That's right. I wanted to answer that. I don't have the answer yet. But I haven't worked on it very much. Probably you can figure it out.
Yeah.
Okay.
Any other question?
Just a very naive question. So when you try to play with this series, you take G 2n plus 1 as some constant divided by 2n plus 1. So I'll just say, have you tried, say, I take G 2n plus 1 to G divided by 2n plus 1 to power of 2 or some other theory?
Yeah, I know. I mean, it's a vast game here.
Yeah.
It's kind of, like I said, I think it's very interesting program to try to, how, presumably not everything works here. Not everything's going to lead to something sensible. But on the other hand, I mean, this is the C/D factor that the, Smirnov and Zemlachkov tell us it is. So you can play with it and put in something else here. It's a very good question. I mean, certainly we could lead to a different, a different kernel. It's gonna, if you change this, you're not gonna have 1 over Koch. You're gonna have a different kernel, and that would make the ultraviolet properties different. So that's a very interesting open question. Like, what freedom what all the choices are there here? How many? Is there only a limited number of choices that are physically sensible and have an ultraviolet completion?
And related to this question, so you mentioned that the Sinch-Gordon its S matrix is actually a CDD factor.
In a way.
Now, in a way, so can I expand that CDD factor in the family of some logic of CDD factor and then fix this GS?
No, well, that's also a really good question. I mean, I think that was kind of motivated what I was trying to do here, because that's a pretty central question. Because if I, in experimental long term, you find this expression, okay, it satisfies all the constraints, of unitarity crossing for CDD factor, but what we think of as a CDD factor is the basic building blocks are usually the Sinch-Gordon-like S matrix. That was clear in Tiago's talk. He considered a pretty wide class of these kinds of CDD factors. They definitely cannot all be written this way. I mean, this has a very limited domain of convergence. So I think you have to go through what I did with this factorization. Okay, so which you can't do in the massive case. So this is important, I think. In the massless case, then you can factorize this and then just require that it converges, say, for positive theta, and then everything is going to make sense. But in general, this has a very limited domain of convergence.
I see.
But through this factorization, etc., I did get it to converge to this 1 over cos theta. Look, the CDD factor, it's still a lot of these things are still a lot of open questions. I mean, like Musaro-Simon's original paper, they just multiplied the Sinch-Gordon S matrix by -1. Now, how do you think about that? Okay, well, one way is with a -1 tells you you're talking about Ising model, like free fermion. Then you multiply it by a CDD factor that is of Sinch-Gordon type, of the type that Ferrari was talking about. Then in this community, you would say, well, this is some irrelevant perturbation of Ising. But which one? I just told you 2 irrelevant perturbations of Ising that have a well-defined ultraviolet limit. Based on the Musaro-Simon analysis, those are c-theories. So those sort of standard type CDD factors, CDD deformations of Ising, have ultraviolet singularity. So they're essentially a bit sick. Okay. And they cannot obviously be written in this form. Even so, but I think it's a good question.
We will move to the next speaker. Let's thanks again, Andre, again.